Is there audio for anyone right now?
Can you hear me?
It's very muffled.
Yeah, it's very muffled.
I can hear you guys great. That's all I care about. It's like, all
Oh,
right.
there we go. That's better.
Oh, it's better now? Okay, yeah, let's see, it's better now? I just moved the microphone closer, so. Is
Yep,
that
it's way better. Thank you, Professor.
Yeah, perfect.
okay? Now you can hear me mumble as I try to go through this. There's a lot of links here. Open all of them, yes. And then there's some other, actually, I went through this other paper and then I got all the way through it. And I had found this paper first. I thought, well, it doesn't have that much to do with, it had something other added features that we're not covering yet, maybe we'll never cover. So, and then this other paper I had, but it's kind of like boring. So I thought this paper, then I went back and redid this paper. So I kind of dumped this, put that paper up here anyway. So anyway, so we won't look at that. Then let's see. So we got this guy. What does this say? Make Chrome faster. Is that a good thing? What's the disadvantage? How about no thanks? Just because I don't trust you. All right, so this is about something called coacervates. So this is like we were doing some work with Procter and Gamble, and then all of a sudden they were only interested in coacervates, which is like, all right, so coacervates are kind of like goo, like phlegm and stuff that you have in your throat, or any kind of goo, biological goo is basically coacervates. So proteins are polyelectrolyte side. So you can have like a positive charge as a polycation, and then negative charge chain as a polyanion. If you mix the two, they kind of bond. And it's in water, and they kind of make something like phlegm. Okay, so this is the phlegm science and the goo. They used to say when polymers first came around, they said it was goo science. So this is like the phlegm end of goo. Anyway, so anyway, there's a wiki page on coacervates, and then so it's kind of a biological thing in a sense, because you get like you can get these gooey droplets of things, and they can, I don't know. Anyway, so that brought people into the idea of primordial soup is part of this picture, this coacervate thing. So supposedly, like before there was life, I think Darwin said that the Earth was a warm soup, like the oceans were a warm soup of all these chemicals, and that these kind of coacervates could just form. And if you look at kind of what they look like, a cell almost, so the idea was like that's like primordial life, is this kind of coacervates coming together and sticking somehow, making things happen. Anyway, so there's a lot of different angles to coacervates, but there's also like consumer products like hand cream things and stuff like that. If you want to have properties change. So you can, so they have a drastic change in properties with changes in some kind of conditions, like temperature, for instance, can break them apart. So they can become viscous, like less viscous at high temperature, and then they can turn into like a gel. So you can have these transitional things due to this bonding of the plus and minuses. And then this paper, he's talking about in adhesives for like if you have an operation and you're going to have an adhesive inside to block yourself from bleeding to death somehow, so you can it turns into glue once it goes into your body. So these are going to be like chains with charges on it. So a sulfonate group. So this is an acrylic group. So acrylic will be like a super absorbent or something if you just have acrylic and a hydroxyl here, like a hydrogen for that oxygen. And then it's an acrylic, like polymethyl methacrylate would have a methyl group here, and that's plexiglass, like fake window glass, whatever. And then you can stick, and then the bio things are just going to be acrylic, like this group, hydrogen, and then that can make, like if you polymerize that and cross-link it, you can make a super absorbent gel from it. So you can, it basically will consume some like 50 to 100 times its mass in water. So you can use it in agriculture to stick the water in the dirt, mix it in with fertilizer or something. And you can use it in diapers. Like one of the main uses is diapers. So if you break apart a diaper, like a Procter & Gamble diaper, Kimberly-Clark, and shake it, it'll be like a white powder that comes out. And if you collect that, and then just take like a salt shake of it into a bottle, it'll like fill the bottle with gel. It'll just completely gel the thing. You know, so it absorbs super, super absorbent. Anyway, so this is stick a sulfate group, polymerize that out. So it's linear, it's not cross-linked. Well, this thing just like loves to go into water. Or the sulfate group, like, so this part is kind of like our surfactant, like you have a oleophilic chain and then a polar end group. And then suddenly this starts to look like PEO. So what this group does is they stick PEO. It's like 2 carbons and an oxygen, which is a water soluble component of pluronics, right? Or oximers, which is here somewhere. So let's see, glassivate, permeable soup, persistence of adhesive, this kind of business, polyximer here. So this is the thing, this is the pluronic thing, this stuff. Right. So this is a non-ionic surfactant. So you have this part is hydrophilic, it goes into water. The propylene oxide is hydrophobic. So then that thing will be like a surfactant. It's got a kind of a non-polar group that goes to oil and a polar kind of a other group that goes to water. Right. So, right, so he's going to stick that, and then so like a non-ionic surfactant. This is like a common one, this Triton X100. So it's got PEO here, hydrophilic, and it's got some kind of oleophilic end to it. Right, so that acts as a surfactant in a lot of things, like ink. If you have water soluble ink, so like Sun Chemical, they mix this stuff with ink and water and an emulsifier of unknown origin, and mix that up, and that's basically ink, in paints and things. So you'll see this Triton X100 in everything, not food, I don't think, but everything else. Everything is like a liquid is going to have this stuff in it somewhere. So it's basically PEO is a working unit, and any kind of oleophilic group will work to stick onto that. And so each kind of possible group you could put onto this has been patented. So there's about 1,000 different variations of this, and everyone claims one's better than the other for one application or another. Anyway, so he's using that stuff. So I hope that you can become like, so this whole thing seems like a mess. Maybe you might recognize the acrylic thing. And then this looks like a surfactant, so that should be kind of familiar. And then this thing you should feel warm and fuzzy because you have PEO sticking on the side, which is like your workhorse. Anytime you want to have a hydrophilic thing, that's the thing you got to stick on. If you don't want to have ions. And here he doesn't want to have ions because the ions are the action groups here. They're going to like bond the things together. So anyway, so if you're going to make this injectable adhesive, so there's 2 kinds of adhesives, like there's like epoxies. Yeah. All right. Oops, wait. Here. I don't know. I think I think that's what it means, yeah. But I don't have any idea, actually. I saw that too, but I didn't look it up. It's here. That means copolymer here. So I guess you just period. Usually you wouldn't have that. It's a good question. I don't know. But I think it's just the way he drew a copolymer. So it's, all right, so he's going to use raft polymerization to make these. So you can, it's a polymerization. So usually free radicals, you have a double bond and then you have a free radical. Initiator is going to pop the double bond, it opens, and that's a free radical. It goes after another one. Then there's just this rapid kind of feeding fest of free radicals attacking other free radicals. Free radicals attacking all the double bonds in the system. So it's like the wolves going after an animal, it's just ripping it apart. So you end up with this polydispersed group of polymers, all different lengths, which is polyethylene, basically. Polydispersity index 14 for polyethylene. So that's the kind of like the second, or the weight average by the number average molecular weight ratio gives you a measure of how broad the distribution of molecular, and 14 is as big as it gets. 14, 16 is like your normal polyethylene milk jug. So these things are going to get one. In other words, there's only one molecular weight that's made from this. So to do that, they take the same reaction, this kind of wolves feeding, but they take the wolves and kind of put them in cages that open periodically so that the wolf can go eat and then close up again. So it's got kind of a protective thiol group that protects the free radicals as they float around. So raft polymerization is really popular because these are like the workhorse polymers, like acrylic. And you can do it with ethylene, styrene. So you make monodispersed polystyrene, whatever, one molecular weight. The only other way to make monodispersed polymers is by ionic polymerization, anionic or cationic. And that you have to, because the ions will just disappear if water or oxygen gets into it. And you have to use catalysts like boron trifluoride etherate, which is, if it hits water, it makes a cloud of HF. One drop of HF will dissolve all the bones in your body. It's like anionic, cationic, like nasty catalyst systems, and they have to have super controlled environments to do the reaction. That said, like almost all tires are made of anionically polymerized butadiene, like the sidewalls. The treads are sometimes isoprene, like natural rubber, which is biodegradable, by the way. But then the sidewalls are these block copolymers made anionically. So there's huge factories. I mean, it turns out like on a lab scale, it's tough to get it clean enough to do the anionic because you have so much surface area to a small reactor and you're only making a small amount because you don't want to have a lot of waste. But on an industrial scale, so you have like room size reactors, there's no surface to it. So it's much cleaner reaction on the small scale. So it's much easier to do anionic polymerization in a room size reactor than it is on a lab scale reactor. So, and anyway, the safety is still there with the catalyst. And generally it has to be run at low temperatures. You need like the whole room to liquid nitrogen temperature. So there's a couple drawbacks to it. So this thing doesn't have any of those. This is not sensitive to water, oxygen. So you can run it anywhere in your bathtub or whatever, and you can just make these things, monodispersed polymers. So everyone loves this reaction. It was invented by a guy at Carnegie Mellon with a name that begins with M, and it's kind of like a Czech name or something that I don't remember. Anyway, so, but I think he won like some prize for it. Not the Nobel Prize, but almost, because this raft polymerization is so popular. So these guys use that. They're going to make these anionic polymers that way, and then they're going to put in. So the problem with these is that so they're going to be like liquidy when they don't bond, and they don't bond when you can put in enough salt to screen the charges. So it's going to be a concentrated salt solution of these anionic and cationic polymers mixed together. And once it goes into your blood's a much lower salinity, so there's less screening. So then the charges can start bonding, and it makes a glue, it makes a pressure-sensitive adhesive. So basically, there's two kinds of adhesive. One's like reactive, like epoxy, and it's going to make a solid after. So you put it in liquid, it's two kind of monomers or oligomers. It's very liquidy, and then or even siloxanes are like that too, like bathtub caulk. So they're liquidy, and then they'll react and they make a network. And then in epoxy, it makes a glassy network, and siloxanes, it makes a rubbery. So they're both kind of adhesives, kind of reactive adhesives. And then the pressure sensitive are like Scotch tape, so you push on it and it'll stick, and it kind of fills in the gaps. And then it's a combination of the flowing ability to fill in the gaps, and then so it's a viscoelastic properties that make it work. The elastic part makes it stick, and the viscous part makes it so you can push it and make it get into the surface. So you want to have both viscous and elastic in these things. And so that's kind of what this stuff will be. Anyway, so once it gets into your body, the salt is diluted down, and then they can bond together. But the problem is, like, because it's got so much salt, it'll burn you when you inject it. It'll burn like crazy, right? Because it's got too much salt. So the salt kills your cells or something. It's not good for you. So anyway, he wants to. So a group tried to do that by putting on a hydrophobic side groups, and then his twist to this. I think it's him. I shouldn't say that, but I guess it's a her. I say in the homework him, but it's her. So anyway, they put on it, their twist is they're putting on a hydrophilic side group, and they pick like of their toolbox, like the first one in it is PEO. So they just stick that on. And they do it with this raft polymerization, which is this a thing that describes raft polymerization. Not that. This is a raft. So it's got these thiol groups that block off the free radicals. He's got a movie on this wiki. Like, I just have wiki links. But this is supposed to tell you how this works. I think the green ones are those are the thiols that are going to block the free radicals. Then the monomers, maybe the blue ones are monomers. I don't know, somehow it's showing how the polymerization works. Oh, the yellow are free radicals. The green are the thiols, and the blues are the monomers that are going to polymerize. So you'll end up with monodispersed. Like, you'll have three groups that are the same length at the end of it. I mean, I'm not sure this helps any to watch this. It's kind of fun to watch them dance around, I guess. Somebody thought this was instructive, I guess, at some point. So the greens won't react with each other, and then it ends up everyone's 4 long. But we'll have like 100,000 long in the polymerization. Anyway, just kind of know the word rat. I figured there was a question like, what is it? It's just something pretty simple. If you want to go into more detail, you can if you like chemistry, but it's kind of a neat concept, you know. Oh, it should say who invented it, right? This guy, who is the guy? History, 1970s, scientist, da da da. Doesn't give that's not him. Doesn't give the guy's name here. I mean, maybe he's forgotten by history. Should be one of the first papers, but not that guy. This guy. This is the guy. I don't know if that's Czech or what. It's Polish, right? Probably. So, anyway, so that's the guy at Carnegie Mellon. I mean, in the end, he had like a huge, like half the chemistry department there or something, like a big group, maybe 50, 100 people, like, you know. Yeah.
Which tab was that? So I can go back to the jet. Is it tab 5 on that or on this page?
Oh, the paper. It's this thing. Yeah. There should be more papers by that guy, but I think it's the right guy. But anyway, maybe I'm not really a chemist, you know. So anyway, so we have. So there's that. And then so this business about the screen of the charge. So you talk about this Debye length, which this is a lot to read, but there's just one equation in here that matters, I guess. The Debye screen like this equation, right? So N is the concentration. I don't know whether to use a different symbol, but N's the concentration of the counter ions. Q is the charge of the counter ions. Dielectric constant of free space and temperature. So it's square root of 1 over the concentration. So the more you put in, the smaller this length becomes, means the charges can't feel each other over a further distance, right? This Debye screening length is one thing, and then there's a thing, and you can write it in terms of this thing called the Beaucage length, and he does that in here, which is almost the same thing. It's got to do with the distance that a charge can see another charge. But the Beaucage length says, like, so you have the charge molecules are moving around with KT, like they're just constantly Brownian motioning around, right? So, and then there's a charge. So you have the energy of the charge interaction, which is like Q squared. Here it has E squared. then this energy of moving around. So you can write a dimensionless number that would be like the ratio of those two energies. It's like, in other words, at some point, yeah, the charges can feel, but Brownian motion makes them like move away randomly. So when the Brownian motion energy is higher than the charge energy, that's like where things fall apart. So the Beaucage, I think that came out before the Debye length. So you'll see Beaucage length a lot. And this ratio of the charge squared divided by KT and some other numbers that ends up giving me units of length. He shows temperature dependence of it, but so those are the two main numbers for Coulombic interactions, right? The Debye length, which has to do with the counter ions. This Beaucage that doesn't. Beaucage is just how Brownian motion affects charge, how charges feel each other. So this is a screening effect, and this is just balancing out diffusion and free energy thing. So anyway, so that kind of, he never mentions that it's the Debye screening length that's the parameter of interest here. That's another thing that's kind of weird, but neither did the other paper. So it's kind of like, well, you should probably mention that, you know, and then show a plot of 1 over square root of the counter ion concentration or the salt concentration to kind of say how this behaves, but he doesn't do that. You know, he just, or she doesn't do that. Then, so anyway, they just, she's sticking on different amounts of these and trying to manipulate this business about having too much salt in it so that you could somehow make them not have as much salt to still be fluid, so you can inject it, which they succeed in. So obviously, like if you get rid of some of the charge groups, it'll be more fluid. So you need less salt to make it fluid, so you can inject it. The problem is it doesn't bond, like, so you can't beat the system, you know. It's kind of like, there's a question here about explain how this is why something, anyway, they try to do that, but they don't succeed. The paper doesn't succeed in the goal that it initially has, which is to both continue to have the pressure adhesive behavior and also have low viscosity when you want to inject it with high salt concentration, with a lower salt concentration compared to before, right? So anyway, so they make it with this raft polymerization somewhere here. And they do some what was this thing? They do a bunch of different things. This is a synthesis of it. They show the kinetics of the reaction. These are GPC curves. So this I was going to ask a question about, but I didn't. But basically, he calls it SEC here. So there's a thing called so it's called size exclusion chromatography, and it's also called gel permeation chromatography. That's weird, huh? Black and white. That's really weird. I guess it's okay. Anyway, so this thing is, you're gonna have a column, it's gonna be filled with a gel. Like usually it's a polystyrene gel. So you have polystyrene and you put in divinyl benzene, which is a benzene with two, it's like a double polystyrene that cross-links it into a gel. And then that'll be soluble in kind of any solvent like THF, toluene, whatever. And then, so this gel is there's different kind of grades of gels you can buy, and they're in a tube. And then you get a high pressure pump. So it's going to go to like 60 megapascal, something like that. So it's like 600 atmospheres, but it's only got little teeny things. So that it turns out like high pressure is dangerous, but it isn't that dangerous because it's going to be like force per area. So if you have a small area, then the force is going to be small. It's like if you have little teeny tubes that are at super high pressure, it's safe. But if you have a big pipe at super high pressure, it's not really safe. Okay, so the voice of experience. It's like, anyway, so this thing has a huge pressure to pump a polymer solution through this gel. And then you're going to have some kind of detector here, like it could be an IR detector. So there's a bunch of different detectors you can stick onto it. And you can index a refraction detector. So that's just going to give you like how much polymer is in that cut that comes out. And then the polymer is going through at a really low flow rate. So the polymer is kind of like diffusing. So you have this KT motion, Brownian motion, just like the chain structure, right? And then superimposed on that, you have this kind of drift motion that's this super high pressure punching it through a gel, right? So So if you have something really long, and it's going through this porous thing, right? So if you have something small, then this diffusion, it's going to spend a lot of time like wandering around aimlessly, right? And then it's going to have a slight drift to go out. And then, but if you have something very large, it can't fit into all the holes in the gel, so it just kind of has a straighter path. And the larger it is, the faster it goes through. Okay, so if you're going to measure this index refraction versus time, then the big things will come out like right away, and then the smaller things will come out downstream. So this is small, this is big, because the small things can do this meandering path search through it. That's the theory. I don't know if anyone's ever measured that, like figure out, tag one of them and follow it through. Basically, that's the theory for it. And so so what they do is they stick in monodisperse, I think polystyrene. So anionic polymerized polystyrene. So it's only got one molecular weight. And this curve on this thing will be like a spike, one number. And they say that number is this molecular weight. And they say, I made this polymer, that's the molecular weight of my polymer. But different polymers go through at different speeds. So if you use a polystyrene standard, it doesn't match up with your acrylate molecular weight. It's not the same number. So it'll be like a high acrylate molecular weight, it's a high polystyrene molecular weight, but they aren't the same molecular weight. So usually you quantify that by saying it's a polystyrene standard molecular weight. The other thing you can do is you can put a rheology unit here and measure the viscosity, which gives you the hydrodynamic radius. And then you can stick on a light scattering, which gives you the weight average molecular weight. So you can stick on a bunch of different detectors on the end, and then you can get an absolute molecular weight from this thing if you want. And the thing is, you fractionate it to such fine cuts that each image you take of it here is monodispersed because it's been spread out. Like you have this curve, and then it's spread out so far in time, you're picking out like monodispersed cuts of it. So all these numbers that you get from it should be the same molecular weight. The index one and the IR are not going to give you absolute, but the light scattering and the viscosity do more or less. And some of these will have like 5 detectors on the end, right? So anyway, that's what they do here. And then they're given the molecular weights in terms of the styrene standard. So it's not much. So you can see this pretty narrow. These are pretty narrow distributions. So they talk about retention volume is like the time, basically the time it took to go through. So high molecular weights here, low molecular weights over here, right? And then they change the conditions, they get different molecular weights. So that's like the standard, and then they map out the molecular weight versus time, get like the reaction kinetics or something from it. So that's that. I didn't ask a question on that, but it's one of those things that at some point they measure the molecular weight some other way. Oh, they measure also like with the NMR, like you can find the N groups of the chains, then find the mass in it, the mass you put into the solution, and the number of N groups. So you divide the mass N by the number of N groups times 2 or divided by 2 or something. Then you'll end up with the molecular weight of the chains from NMR, from a spectroscopy, right, if you can detect those. So they do that. They compare the two in a table somewhere here. So you can see that the, wherever that is, I think it's table 1. It's like right at the beginning, maybe. Anyway, the molecular, what is it? Switch back to what? Oh, shoot, sorry, yeah. All right, lost me there from that. All right, so, yeah, here, so he's got that, one of the molecular weights he gives is NMR, and the other one's this SEC, size exclusion chromatography, which is called GPC. SEC is something organic chemists call it, and GPC is something that we call it. Gel permeation chromatography. They're the same machine. It's the same thing. There's one other name for it. I don't remember what it is, but anyway, so you see the numbers are different. That's because this is styrene, and this is styrene, and this is the actual molecular weight. Also, well, this is going to be the number average molecular weight, and this is some other average. Maybe they're given, oh, MN means number average. So number average, I mean, did you guys take intro to polymers? So you have, if you have the molecular weights, you have this curve, it's like number per molecular weight. Then you can sum the molecular weights in that and divide by the number. That's the number average. That's like what you call the average number, right? And then you can also say, I'm going to take the the molecular weight squared times the number, and then divide by the molecular weight, the average, this number average one, then that's the weight average, because you're taking the mass of each. So you're weighting more the high end ones, way more. So that's called MW, this is called MN. And then you can get what's called MZ is a third of those. Like you take the cube of that divided by the square, and you get MZ. So these are really like basic normal distributions. You say you have the mean, like the first, second order, the third order, and then the order you want. And then this process gives you, so this will give you the molecular weight squared for the answer in cubed, so you can't compare them 1 to 1. But so anyway, so this is kind of easy. It's just a way people decided to do it. So but this is the second moment to the first, the third to the second. If you want to look at it in terms of moments. And then the ratios of these, you take MW over MN is called the polydispersity index. So that if it's monodisperse, all these numbers are the same number. If it's polydisperse, the bigger the number. So the high end ones are bigger numbers. So MW over MN gives you this polydispersity index, which here is 1.2. So for polyethylene, that's 16. For normal polymers, it's 2. 2's the number you should normally get. So 16 is like an explosion happened, you know, and then 2 is like if you had a kind of a controlled free radical. 1.2 means you're getting towards anionic. So so anionic would give you 1.01. And then this RAF gives you like 1.1, usually something like that. Anyway, so there's a lot to that molecular weight distribution stuff. I'll probably talk about it later. We'll see that over and over again. And then let's see. So he did that business. Like I said, this is kind of a more interesting subject, I guess, for me. But then he makes a coacervate. So he's got a picture of how he does that up above, like just the mixing and everything. Like in here, how he puts the thing together. This is a test for adhesion. So you can have like cohesive, adhesive. Then he's got this is adhesive failure. He sees. Oh, sorry. Sorry about that. All right. So he shows there's a series of pictures of these. Actually, right at the top, right? He shows like it's kind of a nice picture, but it's so small. Like the problem is he didn't account for the fact that this is going to be shrunken when in the paper, you know, and even the resolution isn't good enough. But he shows like cohesive failure, viscoelastic debonding, and adhesive failure. He kind of shows what it looks like. And then the stress strain curves are different for these. I mean, this one would have an extended period of when you pull it apart of stress, and this one has a peak and drops, and this one draws out like a necking kind of behavior. Right? So anyway, he does that test, which is kind of interesting, but it's not the question because we haven't really talked about that. It's a long paper for something that the conclusion is it didn't work. Like, you know, so it's kind of, I guess that's why if it had worked, maybe it would have been, macromoles is a good journal, but could have been like, I don't know, a little bit higher than that. So then he's got these curves, right? So these are the things I wanted to talk about. So this is a dynamic mechanical test. So it's a cone and plate. So he's doing this oscillatory cone and plate thing, shaking it with acoustic vibrations. Then he's got the frequency and he's got the storage and loss modulus. So the storage is the elastic part. The loss is the viscoelastic or fluid part. So loss part is basically the viscosity. The viscosity is the loss part times frequency. And the storage would be the elastic part of the material. Right. So like if you so you can talk about this in terms of viscosity, modulus, or compliance. There's 3 ways to talk about these mechanicals, right? So you have so compliance, like take a rubber band, put a weight on it, and it stretches out. So the amount, the stress on it is equal to the strain times the compliance times J. No, wait. The strain on it is equal to the compliance times the stress. Okay. Or you could say like, I'm going to put I'm going to put a fixed weight on this. So that means the stress is fixed, and I'm going to map out this thing as a function of time. Right? Or I could say, in this oscillatory rheometry thing, I'm doing a fixed strain. I'm doing a fixed strain, and I'm looking at the stress, how the stress comes out of it, like the response is the torque and this thing. So I move it a certain amount, and I look at the torque, right? Then I need the modulus, right? Or you could say I have the strain rate times the viscosity equals the stress, right? That's like a dynamic measurement. Okay, so anyway, that's the thing that we had, like the viscosity, the log of the viscosity versus log of time, or log of frequency is going to be this plateau. So you have the plateau, this zero shear rate viscosity, and then this power law decay. So this is like the low frequency end of things, right? Newtonian plateau of the thing. And then in the terms of the compliance, when you first, all right, so when you pull it, and then if you let go, it won't come back to the same point. So that's called the recoverable, if it's in a shear experiment, recoverable shear compliance. So that's called J naught. So you have the strain that recovers. So in this case, you'd be oscillating it, and you stop oscillating it, and it would spring back, like it would come back. So it has like an elastic feature to it. So that's the recoverable compliance times the stress that you put on it. Right? So you have two like knot numbers, the recoverable shear compliance and this thing. And then the modulus also has this elastic component. If you look at the storage modulus versus frequency, it goes up, it passes the so it goes up with the power 2 in frequency. If you do log, it says G is proportional to frequency squared. And then it goes into this plateau part. So this is called the plateau modulus, G0. So that G0 that you see equals like 1 over J0, 1 over what happens when this thing springs back up. So there's 3 numbers, but only 2 of them, they're related to each other. In fact, they're all kind of related to each other in terms of mechanical response. This is the loss part, like G prime, and this is the storage part, like G prime, this is G double prime. Right, so you have this kind of picture of the way things are. So if you go down to 0 frequency and you have a fluid, then this compliance, so the less viscous the thing is, the more compliance you get from it. So basically the compliance, this 0 compliance at low frequency is going to be 1 over, and it's imaginary because of this, it'll be the imaginary compliance that gives you the recoverable thing. So it's I times the viscosity, times this 0 viscosity, whatever, times the M naught thing. Right, so that thing, that kind of looks like that, right? And then in terms of the, I have notes. Oh, it's like this. That's why I have notes. It's I times, so it's basically the more viscous it is, the less recoverable compliance that it has. The less viscous, the more compliance. Less viscous, the more compliance you get. So that's kind of how that recoverable compliance goes. And then the so that's for a Newtonian fluid. And then for the storage part, oh, that's just J. That's just J for Newtonian fluid. For an elastic, J is this J naught. I messed this up. That's how it is. So you have these 2 parts to it. So if you want to know the total, so if you go to 0 shear rate, you want to know total compliance, then you go, let's see. Then the total compliance at the frequency goes to 0. Is going to be the sum of those 2. So it's like J naught, that recoverable compliance, plus the 0 shear rate viscosity. And this part is the imaginary part. So it's I over that. All right, so the reason why you go to compliance is because it's simpler than looking at the modulus term. But the modulus at low frequency is, when frequency goes to 0, is the same as 1 over the compliance as frequency goes to 0. So that means you can take this thing and say 1 over J naught. There is a moral to the story, then you get that thing. Then if you want to get, but you want to get this thing, so this is a complex number because it's got real and imaginary. You want to get it in terms of I and then plus and not I, right? You want to have like two parts, and this would be the loss part and this would be the storage part. So get that, if you have it down here, you have to multiply by the conjugate, which is minus the I part. And then you can also clear out the ins. So you could do N0 omega and get rid of that here and put it right here. And then multiply by that, let's see, I got rid of that. So I can just put that here. So it's just J minus I. And I have N0 omega here. See, did I do that right? Let's see, I'm missing something here. N0 omega, that's good. J0 N0 omega plus I, then multiply by somehow I did this N0 omega here. It has to be I because then those cancel out. So when you multiply this by that, so if you do this, you just get minus I, and you get that minus I becomes plus 1. So this thing will become, I'm going to write the answer. J0 N omega N0 omega squared plus 1. And the top part will become J0 N0 omega squared minus I omega N0. So this part, so there's no imaginary part here. And this part gives you omega squared, and this part gives you omega. So so G prime is proportional to omega squared. G double prime is proportional to omega. And if you plot those out on log, so log G versus log frequency, then you're going to have like a power 2 for the storage. So they cross. So you'll get a crossing point when those two match up. So anyway, kind of ask you to do something like that. That's written out in yeah, that's a dash that works. So if you just Google time temperature superposition, you get this thing. That kind of talks about, anyway, oh, that's not what I'm looking for though. Wait. All right, so there's there's a lot of stuff. So this is 2 pages from the Strobel book. The whole book is there, but this is basically what I just did. Like he just kind of, well, I didn't do it very well, but he does it here. Basically this page, like storage is that, loss is this. Then he writes the storage is the modulus 1 over the compliance. So he takes this expression, he gets this expression by clearing the N omega. Then he multiplies by the complex conjugate of that to get this thing. And then he finds out that this thing should be that thing squared. This is that thing straight up. All right, so if you look at the paper, he's got 1 and 2 here, right? So that's our 1 and 2 from that whole schmazzle thing we just did. Right, that's the reason you always so this is Newtonian flow. Basically, that's low viscosity, not this viscoelastic flow at low shear rate. So you have power of the store and loss modulus go 1 and 2. Then you have the crossover point here, which would normally be the time scale of the system. Right. So this is interesting because it has, right, so normally you expect the storage to go above the loss there and then plateau out, and the loss would drop. And then you'd have a plateau modulus, which would be the modulus of chains that are entangled at the entangled points, and that makes a rubber. So that's the modulus of a rubber that has chains that are entangled. On the time scale, the entanglements can't relax, then it turns into a rubber. So you'd have a plateau of the G prime, and G double prime would drop. That would be the normal behavior, but this behavior goes into this 0.5 thing, right? So And there's two features here. One is the slope is 0.5, right? And the other is that the behavior of G prime and G double prime match each other there. So they have the same behavior. In fact, they have the same value. They both have this 0.5. So this is a thing in like kind of, I think around 2000 and 1990 something. Let's see, I have that paper here. This guy Winter figured out what that was, like why that happened. Henning, Winter, and Chambon. So it's called a Winter-Chambon theory. This paper isn't particularly readable. So he's doing gels and he finds out, oh, the things match out. So it's a gel. It means it's formed a solid gel. That's called the gel point in the rheology behavior. And if you go above that, you see when he goes above that and so he's curing gels across here. So this is at the gel point. This is when it's a sol, so it's a liquid. And then this is where at the gel point. And then when it gets to being above the gel point, you see there's some point in frequency where it goes to the gel, goes to that 0.5 again. And down here you have the 1 and 2, more or less. And that's seen better. And this thing, probably was sort of linear, but that's not it. And not that thing. Shells and liquids. This thing on page, does it say, what's the title here? I think it's like page 19, if this is the right thing. Page 8. Page 13. There's a lot to this, you can see, and people are kind of interested in it, but because gels are everywhere, but here. So this is Winter's plot kind of redone or something, but you can see you go from the gel point where it's 0.5, and then above that you have a 0.5 region, meaning it's still a gel. So it's cured more, it's like a more solid gel, and then it's got that liquid behavior and gel behavior. So there's a time scale where this adhesive becomes like a gel, like it glues together more or less. So anyway, if you see that in a dynamic mechanical, it's a signature of a network. You formed a network when the two things match up and they have a 0.5 slope. And that's called the Winter-Chambon behavior or something. I'm not sure he mentions that in here, but that's what it's called. So it's kind of interesting he's got that. Then the other thing is that these are, let's see, these are at different salt concentrations. So he goes up and so he has the C82 means, so the CE100 means it's 100% with none of the PEO sides in the block copolymer, the anionic polyanion. And then he reduces she reduces the amount of PEO in it, and the viscosity drops. And then these are different salt concentrations. And you can see the kind of the behavior changes as you add more salt, reduce the salt. So the top one is the least amount of salt, and the bottom one is the most amount of salt. And you get to this kind of classic behavior here. And then the other thing is that these are time temperature superposition curves here. So this AS frequency thing means that he shifted it to, so he does different temperatures. So you have, all right, so yeah, this paper's a lot of stuff. All right, so you have like the viscosity is going to be equal to some viscosity at some temperature, say T, then exponential of the temperature of like exponential of like KT, E, let's see, energy, like an activation energy over KT. Right, that's called Arrhenius. Or it also looks just like Irene rate theory, right? So you have that's like the basic thing. And most things, like even polymers, if you look at the viscosity versus temperature, it behaves like that. So you have this energy of activation thing. So you could, right, so you could talk about that as you could take like ln of n over n0, and then this is like a shift factor. Or this thing, I guess it's just n over n0 is this shift factor, AT. So AT is going to be a temperature. You can plot AT versus temperature, and it's going to have, let's see, this is minus E over AT. So it's going to be AT over temperature. Temperature goes up, this should drop, right? So it should kind of look like that or something, right? It's not a linear thing, right? So anyway, so that works pretty good. You can use that for polymers, So it's got one parameter, right? And then people realize like as you cool down near the glass transition, you don't get viscosity goes to infinity. So it's a problem. Like this thing goes to infinity at 0 Kelvin. Right. So they added in a thing called a Vogel temperature. So you have T minus TV. Right. So that's 2 parameters. That's one simple modification to this thing. So you have a 2-parameter equation. And then I guess maybe people realize that you need another parameter, but really the energy, so if you have like the free energy, it's going to be the enthalpy minus a temperature dependent term, which is entropic TS, delta S, the entropy, right? So basically that would be another parameter. So you'd have exponential of minus delta H minus T delta S over K times T minus the Vogel temperature. So you have 3 parameters to get the behavior of, say, a polymer fluid. Right. And then if you want to know the viscosity, it also works with the basically any of the properties going to behave like that. Right. So this thing you call like the shift factor AT. The most common form of this thing is like this. Is this WLF equation. So this is temperature, WLF equations here. So 3 parameters also, T naught, which would be like kind of our TV, C1 and C2. So they have, so we have delta H minus T delta S over K times T minus TV. And they have, what is it? C1 times T minus T naught over C2 plus T minus T naught. Right, so if you take C2 minus T naught, so if you this thing TV would become T naught minus C2, right? And then this thing C1 times T, so delta S is C1, and then C1 times T naught is delta H, right? So you can say like this is like the entropy, basically C1 entropy of the trend of like say the motion that you're looking at for viscosity. There's some organization that happens when the motion happens, so entropy changes, something like that. And then this is the enthalpic part. There's an energy involved in moving through a fluid, and this is because you have a glass transition. And so it's kind of reasons for them, but basically, if you want to broaden out your viscosity measurement, so here's the AT. You want to broaden out the measurement of modulus, and so you run it at different temperatures. You can see those different curves here combined, and he shifted them with this shift factor, right? That he calculated from these shift factor numbers. Oh, sorry. Sorry about that. All right, so he's got, you can see he's got this line, that line, and that line. So there's like 3 different measurements he did at 3 different temperatures, and then he shifted them with that shift factor thing. So one of the main things he's talking about in here at the beginning, he says, all right, so this means that if they fit like that, if you can shift them like that, that means that the mechanism that's involved is the same. Like, in other words, for the simplest case of viscosity, you have a bunch of spheres and you move another sphere through them. So the spheres have to move out of the way. There's a simple energy of doing that. And when it does that, maybe there's an entropy involved in doing that. The organization has changed. And then also, if the thing has a glass transition where everything gets stuck, well, that's the endpoint. So you have to put that in. Now, so this is kind of like modifications to Arrhenius, like simple modifications. And it worked like those 3 parameters, you can describe everything. So it's kind of like a 3-parameter deal. But actually, if you try first the Arrhenius, it'll describe almost everything. So it's only rare cases actually where you need this WLF. So it's kind of like there's excess parameters in this thing. So what he says, what she says in this paper is that, well, because I see this behavior in temperature that I could shift this, but here I have a dependence on salt, so I can shift it. I can use the salt concentration as a shift factor too. So she comes up with a shift factor, mimicking this time temperature superposition, but we're using salt because salt has the same effect. It just shifts the curves. And she says she can use that to get a master curve. And because she can do that, then she can say that, and this middle one is that master curve thing. It's the same mechanism. She's just tweaking it. Like it isn't changing the mechanism to add in this, to add in these groups doesn't change the mechanism. right? In other words, the same kind of association between the chains happens. It's just I'm reducing the number by sticking these things in here. So it's kind of a little bit of an esoteric thing. And also, both in terms of salt concentration and in terms of number of these polyethylene oxide units she sticks on. So you can do shift factors that are dynamic mechanical with both of those things. So it's kind of interesting, you know. It's of limited use, but basically an interesting concept, I guess, you know, more or less. But so it's quite a bit talking about that, and there's some talk about the gelation point and this stuff. It's a lot in this paper. I mean, any of them. So at this point, like everything we see is going to be like a new. In the end, if you read the conclusion, they say they kind of subtly say like they couldn't. The adhesive properties go to hell. So it's like, yeah, we can get a lower viscosity, but you can't get the thing that you want it for. So you could jab it into someone at a lower salt concentration. It doesn't burn, but they die from bleeding. You know, so it's like, well, didn't really solve the problem. Anyway, so so what's a coacervate? What's a pressure? Maybe you could say like, what's a pressure sensitive adhesive? Debye screening, say something about it. I put some links there. And then let's mention Pluronics, PEO. So where's the PEO in this thing? It's just like find that picture and say it's there. Like that, there's that picture of the molecules, it's there. It's the same. So it should be PEO should be like a friendly thing to you now. Like, oh yeah, I know PEO. It's and then you see this complex molecule. Oh, it's just PEO. They stuck on it, and I know why they did it. It's hydrophilic. No, and they even say it's hydrophilic. And then maybe use a cartoon like from last time. Like try to draw a cartoon to explain like what's going on, like how their scheme works. You can kind of copy their cartoon. It's a broad acceptable range of answers here, but just try to think in terms of cartoons instead of the molecules, like how it would fit together. Then like what's RAF polymerization? Just go look at the page and the guy's dancing. You can talk about that, or you can talk more about thiols. The drawback is that thiol, I guess, thiols are toxic. They're neurotoxins. And also they stink. Like a small amount goes a long way. There was a refrigerator down on the 4th floor of Rhodes that assignment at do not open because they were doing because you use thiols to sulfur to cross-link rubber, and the guy's doing rubber work. Then he died, got cancer. And then so the refrigerator was there for like 20 years. It just had a sign at do not open. The guys inherited the lab. So the whole lab's nice and clean. There's this white refrigerator in the corner, do not open. Of course they opened it. It's like, and then the whole lab, like it took like weeks to vent out the thiol smell, which is a neurotoxin. So it's kind of like bad to have around, especially if you're a PhD student, you know, you kind of rely on your brain a little bit. But, so anyway, so it happens. There's worse things that have happened. Like, all right, my advisor, so he had one of the other professors, it was before I got there, but so a student was like complaining of headaches and stuff and like having neural problems, like features of whatever's going on. And like 10 years later, huge pool of mercury under his desk, like where he had sat, you know, but it was too late. It had gone by. And even like in the old days, they didn't have, like people are really careful now, but back then, like routinely professors would pour mercury into their hands and like play with it. Right. I mean, I saw that many times. So anyway, rules were different back then, but the guy did get brain damage from it, but as a grad student. So what is time temperature? So just kind of do the best you can do, just roughly what it is. The Vogel temperature is like the glass transition temperature. Then whatever I did with the G. Oh, there's a paper on this. There's a paper that goes through that business about the glass transitions link there. Like not that one. Wait, not this. This might be worth reading. This is from the rheometer company. And then all right, so yeah, so that's about it, I think, for this. Anyway, there's a link to the that thing. And then linear viscoelastic, there's a link to that too. That's just kind of, that's basically that TA instrument thing. Anyway, so we're out of time. Sorry about that, but a lot of stuff. Any questions or anything? Yeah.
What kind of RAF polymerization?
Mhm.
The style of acquisition.
Yes. Yeah, so it goes, and it's a temporary inhibitor, so it spends time holding onto it and then it releases once in a while. So that it protects it so that the way to terminate is two of those free radicals meet. So it lowers the odds of two of them meeting and terminating. When it terminates, that's what causes the distribution. Because you grow just a short length, terminates, and then then you have short length ones. But if it continues to grow and you never terminate, then that thing can just all make the same until it runs out of monomer, they'll all be the same length. So that's kind of the idea of it. Right?